Good morning, good afternoon, good evening, everyone, depending on where you are. Welcome to today's webinar titled Adams-VTD Integration. So today we're going to introduce how we're connecting two of our best tools to enable you to do better in the ADAS and autonomous driving simulation. My name is Yijun Fan. I am the Automotive Application Manager at MSC Software. And today, co-presenting with me, we have Peter Grimtel. Peter is our VTD, one of our VTD developers. He's now currently based in Sweden, in California, USA. All right, a brief overview for today's agenda. So first, we will give a brief introduction to VTD and Adams to those who are not familiar with maybe one of those two products. And then we will go through, briefly go through the driving simulation workflow to see a bigger picture and how those two tools are supposed to work together. And after that, we're going to go through some of the benefits of why we should connect or why we should integrate Adams and VTD. Followed by that, we have an example showing how we are actually connecting Adams VTD through a semi-truck example. And at the end, Peter will take over and give you a more detailed demo of the actual process for setting the whole thing up. And if you have any questions for today's presentation or for Adams or VTD, please use the Q&A window to type the questions in. At the end of today's webinar, we will have about 5 to 10 minutes Q&A session to answer your questions. If we cannot get your questions answered during those times, we will follow up via email. Okay. So to those of you who are not, I know there are Adams users who are joining today's webinar. So for those of you who are not necessarily familiar with VTD, so VTD is our open platform for the basically creation, configuration, and anything to do with ADAS and autonomous driving simulation. VTD is an open platform to capture all of those elements. For example, all the sensor models, all the vehicle models, and also different scenarios, weather, road condition, everything you need to represent a vehicle in a virtual environment for ADAS and autonomous simulation. VTD can deal with all of those. So it's basically an open, comprehensive platform for you to do or perform those analyses for autonomous and ADAS driving. A brief intro to our team for VTD, our development team and the product team. So Marius, he is our managing director for VTD, and the team is currently based in, mainly based in Bad Aibling, a place close to Munich, Germany, and they have over 20 years of experience with ADAS and autonomous driving developments. And as we know, VTD is one of the co-founders for the open standard movements. So these standards are used to define things like the, those are an open platform or open formats to define the road network. An open scenario is used to define the scenario. So when, for example, two different companies or corporations or organizations, if they're creating those scenarios within the same file configuration, those files can be shared among or between each other. In OpenCRG, as we all know, it's also used in Adams as well. It's a way to define the road surface, especially for some of the rough roads. VTD also is a partner in a number of research projects related to ADAS and autonomous driving. So they have been doing that for a long time. And VTD is also being used by a number of major automotive OEMs and also autonomous driving research and organizations and companies. It's one of the industry standards now where we deploy for ADAS and autonomous driving. And then to those of you who are not familiar with Adams, so Adams is the world's most widely used general-purpose multi-body dynamic software, which is used to simulate complex mechanical systems with moving mechanisms. So it's the gold standard for multi-body dynamics in the industry, and it's being used by basically across different industries, from aerospace, machinery, automotive, all the way to medical devices, oil and gas. So it's Adams by itself is a general purpose multi-body dynamics tool. And there's a product inside Adams which we call Adams Car, and that is specifically developed for the automotive industry. And it's a highly customized environment for you to create and analyze your vehicle, the full vehicle model, multi-body dynamics model, or perform vehicle dynamics analysis. And in the automotive industry, Adams is also quite prevalent. It's being used by 24 out of the top 25 automotive OEMs on a daily basis to do vehicle dynamics analysis or various other initiatives and projects. So typically in the vehicle dynamics area, there are three different categories that Adams can be applied in. First is the vehicle handling and steering. That is relatively in the lower frequency range, we will say. And the next level is the vehicle riding comfort, which is a bit higher frequency than the vehicle handling and steering, but it's still considered to be a very important task. For example, if you want to analyze how the vehicle is going to behave, or what is the acceleration under the passenger seat when the vehicle is driving through a rough road. Well, these are the very typical scenarios to apply the Adams Car in the ride and comfort events. There's also road rules generation. Usually we apply the highest fidelity vehicle dynamics models with usually multiple flexible bodies and F tires, high fidelity tires, and these are used to generate the loads that will be used subsequently for stress and fatigue durability analysis. And usually these requires the users to acquire a very good correlation with the physical test before they're being used to generate virtual road loads to be used later for the durability study. So all these three levels of events or scenarios are how Adams Car is mainly used in the vehicle dynamics area right now in the industry. Now let's take a look at the bigger picture at the workflow of autonomous driving simulation and see what are the necessary elements needed in order to perform this analysis. As we can see on the left-hand side, this is what VTD provides. It's a complete open platform for you to include all those elements in this 3D environment. And on the right-hand side, for example, the first box is sensor fusion. Those are usually where, for example, the perception engineers, this is their area of work. And so after they get all the information from different sensors, from virtual sensors, they will find a way to do sensor fusion and how to interpret those results from different types of sensors. And based on those, it will be provided to the actual control algorithms or AI driver in the way that it will decide what is going to be the path going forward. How to, for example, how to go get over a obstacle, or if there's a pedestrian walking in front of you, how to react to that. So based on the perception that the engineers or the computer is getting, the AI algorithm or the actual controller will decide what is the path planning, what is the path going forward. And after that, it will give out a list of functions to actually control or actuate different parts of the vehicle, for example, the steering systems or the brake or the acceleration. So then it will give those signals back into the vehicle. And the vehicle model inside the VTD environment will take those signals and then decide how the vehicle is going to behave based on those steering inputs or based on those gas pedal inputs and things like that. So that's actually a very important element, because when you are talking about driving the vehicle on a straight line on the highway, you probably don't need a very sophisticated or very complicated vehicle model. And we have embedded vehicle models inside VTD that can handle those very well. But if you're driving the vehicle, for example, on the Belgian road, on the rough road, or you're driving the vehicle over a speed bump, then those are going to change the way how the vehicle behaves. And the complex suspension system, and also how you're going to take into stiffness and damping coefficient into account, how the chassis, how the steering is going to react. When you are working with those more complex issues, and if you want to see how sensors are reacting to that, then you will need a more complicated vehicle dynamics model, and that's when Adams car come into play. And to follow up with what we talked about is the benefits of using Adams car in the VTD environment, or the benefits of connecting Adams car with VTD in one workflow. So here are some of the benefits. As we briefly mentioned before, so first, Adams can be used to represent the more advanced vehicle dynamics models. For example, driving on a rough road, driving over a curb, doing any evasive maneuvers. And secondly, with those more complex vehicle dynamics, for example, when the vehicle is driving over a curb or an obstacle or a speed bump, you will actually see that with the real vehicle, the sensor is going to vibrate. The sensor is going to behave differently than what we call the ideal sensor or the perfect sensor. So in these scenarios, an engineer who works on sensor positioning or sensor location optimization might want to analyze what is the location to mount the sensor that will have the least vibration in all these different scenarios. So having an accurate vehicle dynamics model is going to be essential for those tasks, as for example, sensor positioning or even sensor fusion or interpretation. The next application where we see this will fit is in the driving simulator. As you can see here on the screen, this is rather simple driving simulator, but if you're talking about those multi-million-dollar driving simulator, which has a very complex chassis and suspension system, then usually what we can expect is that the chassis will move from in order to react to the actual driving behavior. So with a more higher fidelity vehicle dynamics model and a more accurate chassis simulation, you will be able to capture all those movement in the suspension system in order to, say, give a more realistic driving behavior to the driver and study how the ride comfort is going to look like with different chassis design or with different suspension design. So these are some of the benefits of using Adams and VTD integration. So you might be an Adams engineer or you might be an autonomous driving engineer. From both sides, we do see an occasion or benefits of joining those two solutions together. Of course, it's not going to be necessary for every single autonomous driving scenario simulation, but for some of the more complex behavior, we do see strong benefits, or we do see this as essential to integrate the two solutions. And next, let's briefly go through a truck example and see some the general process of how those two softwares are communicating with each other in the actual integrated solution. And then we'll go to the demo section, and I'll pass the presenter to Peter after that. So for the semi-truck example here, what we are doing is basically we are exporting the Adams car or the truck model in Adams car as an FMU, and we're importing that into the VTD. So in this case, we're using the functional markup interface connection, and the VTD is the master and Adams car model is the slave in this case. And we're performing two maneuvers. The first is the lane change maneuvers. There are going to be 3 lane changing maneuvers at 70 kilometers per hour. And the second scenario is a brake maneuver on the highway. So that's the first scenario or maneuver. As you can see, the vehicle is going through. The first is the lane change, and there's going to be a second lane change. And in this case, you can see This is the VTD environment, but the actual model or vehicle dynamics behavior is being powered by Adams, and doing a very abrupt lane change after that. So that's how you're going to see from the animation. Those yellow wireframes, those represent the sensors that are mounted on this vehicle, and those are defined in VTD. A quick look at the Adams car model for the truck. The number of degrees of freedom is 310, and usually in this case we will want to make sure that the Adams car models are real-time ready, which we have hosted a number of webinars before talking about the Adams real-time capabilities. So basically there's a real-time integrator or the fixed step integrator that we are implementing, along with some other real-time capabilities to make sure that your Adams car model is real-time compatible. And in order to do that, usually we don't include any flexible bodies, and we use a rather simplified, for example, anti-roll bar. And typically we don't include complex tires like F tires into those simulations. We use PEC 2002, and there's also a capability in Adams called model reduction, which will enable you to reduce some of the more complex parts into a rigid or simplified part configuration, so that you can make your Adams full vehicle model real-time compatible. So for more details of those, please refer to some of the webinars we hosted before. And there's a special feature that we introduced in the recent Adams 2019.2. It's called the Adams Car FMU export to VTD. So before, as you know, when you're going through a simulate and FMI interface, you would generally you can create FMU export. But in this release, we created a special portal for us to export an FMU to VTD, so it can be read directly into VTD for the process. And we can also define all the inputs and outputs in the communications between Adams and VTD in this FMU export. You will see more details in the demo later in the section. And in this case, the Adams model is on the left-hand side and the VTD model is on the right-hand side. So what we're doing is that we're inputting where there's a number of parameters that's being transferred between the two software or between the two tools. For example, VTD as a comprehensive environment simulation platform, it will give basically signals to Adams as to how the steering, the brake, and throttle is going to react based on the current environment. So that is the control logic that's included in the VTD platform. So you can, of course, you can define your own control algorithms inside that. And based on those signals, and also there's, for example, the environment factor. For example, how what is the friction coefficient on the road surface? For example, if the vehicle is driving on the slippery road on a rainy day, on a snowy day, or is it driving on a sunny day in California with a dry road ahead? Those will present different friction coefficients on different parts of the surface of the road. So that will be defined in the VTD, and the VTD will give those friction coefficient of each wheel plus the signals to control the steering, brake, and throttle into Adams. Based on those inputs, Adams will calculate the vehicle dynamics, how the vehicle is going to behave, all the roll, pitch, yaw for each defined parts in this case, and these will be these parameters or these results will in turn be transferred into VTD to define what is the position, how the vehicle is going to react based on the control signals and also based on the environment. So basically, Adams is embedded inside the VTD environment to provide the most accurate simulation of physical attributes of the vehicle itself. And this goes in the loop as a this goes in a closed loop control fashion. Here's the second scenario we're defining, or event we're defining. As you can see, the small sedan is suddenly braking in front of the big truck, and what this does is that the vehicle will brake, and we can see the obvious pitching effect of the semi-truck. And here we can see the pitch angle for the red curve, which is the cabin, is very different than the pitch angle from the front from the frame itself. It's probably not so obvious because the WebEx doesn't transfer those videos in a very high fidelity. But if you can, we'll provide a link for you to download those videos later after the webinar, so you can see that you can actually tell the differences between the pitch angle of the cabin and the pitch angle of the frame. It was pretty obvious from our computers and screens. So these are the results of a different suspension system, or a higher fidelity suspension system that's going to cause this difference in this pitch angle, which in turn will make the sensor behave differently. So if you are not able to capture that more detailed suspension behavior, you won't be able to actually calculate how the sensor is going to react or behave or interpret the environment in a more realistic scenario. And that's one of the reasons why you need Adams car model in those a bit more complex situations, or where you need to apply the fidelity of those complex or accurate suspension systems into your simulation workflow. Okay, so that's it for my part. Now I'm going to stop sharing and pass the presenter.
So I would like to start off with a side-by-side comparison of the VTD built-in dynamics and an Adams model, in this case for a pickup truck. And the VTD built-in dynamics is based on, of course, a Bullet SDK, Bullet raycast vehicle, which is a 6 degrees freedom body plus wheels simulated as a suspension and tire friction, while the Adams model in this case has 166 degrees of freedom. So we will run a short scenario here, pre-recorded video, and compare the dynamics in a quick lane change, then driving up on the curb, and then going over a plate and a couple of speed bumps. And I hope this video will run reasonably well, so you can see the effects. So first, in the lane change, we will see a slight tendency to skid for the Adams vehicle. And here we will slow down and go up on the curb.
Yeah, again, we will provide the link to download those videos directly after the webinar, so you can see a more obvious effect of the differences between the two videos. Sorry for the choppiness from the WebEx.
So a break, I forgot to mention that, and then plate, and hopefully you can see a bit of a difference there. We'll run it from another view, just the last part when going over the speed bumps from the point of view of the driver, so you can imagine then what a sensor front-facing camera would see. And again in slow motion. Now let's see how this is exported from Adams. So we will start by loading a vehicle assembly of this pickup truck. This assembly contains a high fidelity model of the front anti-roll bar, So we will create a simplified representation of that. Go. We will create it using a predefined tool in Adams Car. The detailed beam structure is replaced with the 2 parts and the torsional spring damper with the stiffness that corresponds to the detailed model.
Here we're doing the model reduction for some of the parts, right?
Next, before exporting the model as an FMU suitable for VTD, we select the fixed step integrator, set the number of threads for the solver, and turn off generation of the results file. This will make the simulation faster. Now the model is ready for export. So we select a prefix for the name of the FMU, and then we set an initial velocity. And there's no need in this case to set any other signals or parts. So the result is an FMU of the Adams car model that can be executed by VTD. Soon enough. Yep. There we have it. Next, to configure VTD to use this FMU. First, I will copy the setup and project of an existing Adams configuration. We have 2 example setups, an Adams passenger car and Adams truck trailer. That's the semi that you saw before. I'll base this pickup setup on the passenger car since it's the most similar one to the pickup. So I just need to copy the folders for the setup and the project. And then rename the project configuration file. Next, I will copy our new FMU into the new setup. The FMU dynamics is handled by VTD's module manager, so therefore I will copy the FMU into the module manager's config folder. Setups, Adams pickup, config, module manager. We copy the FMU file here. And then we have the old FMU belonging to the passenger car. We can remove that. And then we have 2 XML files. One is a mapping file that defines how the signals in VTD connect to the signals in the FMU, both inputs and outputs. And then we have the configuration file for the module manager itself, which will tell it which type of dynamics that are going to be used, in this case FMU dynamics. So we'll start by renaming our mapping file and editing it to point to our new FMU. Here we just replace the name of the FMU. And then we can have a look at what else is in this configuration file. We have mappings for all the signals that are communicated between the FMU and VTD. We have the object state, that's the body, position, orientation, and speed. We have driver control, that's steering input, throttle, etc. And we have outputs for wheel position, angles, etc. for each wheel. And we also have road data input, that's the road height and the friction at each wheel point. So then we need to just rename the mapping file within the configuration of the module manager as well. So this dynamics plugin section of the configuration tells us that we'll use the FMU plugin. It's handled by a shared object file here. So now we need to replace this, rename this file. And that's the configuration part. Next we will start VTD with this setup and project. And select a scenario that we're going to run. We're going to take this Adams car demo, just rename it pickup demo, and edit it to change the vehicle type of the ego vehicle to use a 3D model that will match our FMU. So this is going to be a Ford F-150 Raptor. Case. Save it. Go back to VTD main GUI and just make sure that the correct scenario is loaded. Everything and wait for road data to be loaded. And start. And here we go. So that's all that I had. So I'll pass the word over again to Adrian.
All right, thank you very much, Peter. Let me take back the control. So there's one thing that I do want to mention is that, so we mentioned before that for this particular example, we were exporting and importing everything in real time. But I do want to mention that in order for VTD to connect with Adams, the Adams model doesn't have to be a real-time model. So it can be a if you want to test everything in real time with the real control algorithm and sensor behavior, you should make the Adams car model real time for sure. But it doesn't have to be real-time ready in order for you to connect the two tools together. For example, in some of the cases, you can have a fairly complex Adams model, with a lot of flexible bodies and also with very detailed tire models. and in some cases you can still connect you can still connect that with the VTD. In some cases you only need to, for example, see how the vehicle behaves in those complex environments, or to see what is the riding comfort of the passenger. So you can still do that. Although if you want to capture how the sensor and everything is going to behave in real time, or if you want to include some of the hardware in the loop in the workflow, then you do need to make the Adams car model run real time. And in Peter's demonstration, you can see there are some of the model reduction capabilities in Adams that you can leverage in order to achieve that. So this is also Adams car truck model running behind this, correct?
Correct. And we will see this view with the sensors moving relative to each other when we go over a pretty obvious bump in a few seconds.
Very nice. And this is from an actual scan 3D roll, correct?
That's right.
Okay.
And transferred or converted from the 3D model to OpenCRG for VTD.
Sounds great. Awesome. Thank you, Peter. That's a very interesting demonstration.